Welcome to Experimental Design. In this lecture, I'm going to give a general overview, the general introduction to the topics that we're going to be discussing in this course. And so the first thing I want to talk about here are the purposes of experimental design. Why think about experimental design? Why take a course in this particular topic? Well, when we think about the purposes of experimental design, we can think about it from a prospective standpoint and from a retrospective standpoint. Thinking about it from the prospective standpoint first, some of the prospective purposes for experimental design would include the following. Number one, to design an experiment in such a way that specified research questions, those questions that are of most importance to a researcher, can be answered, and not only can be answered, but can be answered in a valid way. Now, this may seem almost too obvious to be mentioned, but I will say that there are, many situations out there, many examples of situations where researchers have performed experiments only to find out after the fact that the data that was generated by those experiments really cannot be used to answer their primary research questions. The experiment was just not set up appropriately with their research questions in mind. And so, that would be a very unfortunate situation to spend the time and the money and the resources to perform an experiment only to find out that no matter what the data look like, you really can't answer the questions that you wanted to answer. Now, the second prospective purpose would be to make sure that we have an experiment that provides as much information as possible for answering the research questions for the resources used in the experiment. Now, if you are a researcher and you're conducting your own experiments and you're taking this class and wanting to learn something about experimental design, certainly a researcher is wanting to get the most bang for the buck. They're expending time and energy and resources, money and experimental material to do these experiments, to learn something, and then perhaps to publish results. And so they want to have the most information resulting from such an experiment as possible. So that almost goes without saying, but we do have to think about that. And it does take a little bit of work to consider various experimental designs for a given situation. Now, the other way to look at this, perhaps you're not somebody doing your own empirical research or doing your own experiments. Maybe you are a statistician, and you are working as a consulting statistician, helping researchers, empirical researchers, to design their experiments and analyze the data from those experiments. Now, certainly as somebody who is consulting with researchers, it's really incumbent upon you to help to make sure that they are getting the most bang for the buck. It would be really irresponsible, if you think about it, to provide an experimental design to a researcher or recommend a experimental design to a researcher if that experimental design was not the most efficient possible. It was not going to give the most information possible for the resources that they were going to expend. And so from both of those standpoints, it is very important that we consider different experimental designs that can answer a particular set of research questions and look for those designs that give us the most bang for the buck, the ones that are most efficient. And then finally, the third prospective purpose here, to help identify and clarify the research questions to be answered before resources have been expended, before the experiment's been conducted, and before the data have been obtained and seen by the researcher and or the statistician. Now, this obviously ties back into the first bullet point here, and the point I'm trying to make here is that the research questions to be answered really set up certain limitations on the experimental designs that can be used to answer those questions. And so we need to think about that before the experiment's been done. So let's think about this in a little bit more detail. The importance of identifying and specifying research questions before conducting an experiment. So if we think about identifying research questions, the design of the experiment determines the types of questions that can be answered. And so therefore it's really imperative that the research questions be identified beforehand so that an appropriate experiment can be designed. So we really can't, for example, as statisticians, consulting statisticians, we really cannot recommend a design if we don't know the research questions to be answered, because the research questions really depend on the design of the experiment that is under consideration. So you see that dynamic here. We have to identify the questions to be answered, and then that will, in some sense, give us an indication of the type of experiment or the design of the experiment that can be used. Now, let's also look at the importance of specifying the research questions before conducting an experiment. And I'm differentiating between identifying the research questions and specifying the research questions, because we can identify, or a researcher can identify research questions without really specifying them publicly. And so when I talk about specifying, what I'm talking about is specifying in some public way, whether it's in a research proposal or perhaps in a research article where you're proposing a subsequent experiment to be performed. And so let's talk about this. So the importance of specifying research questions before conducting an experiment. And so the reason for this would be that conclusions drawn regarding questions that have been suggested and answered by the observed data. So if we look at the observed data, if we perform the experiment, we look at the data, and that data then motivates us or motivates new questions based on what we're seeing, then conclusions regarding those questions are really not as compelling, and they're not as valid as research questions that were specified beforehand, before we conducted the experiment, and certainly before we saw the data. On the other hand, specifying research questions to be answered before the experiment has been conducted and before the data have been obtained. If we specify those questions up front, for example, in a research proposal that we write up and we submit before we ever do the experiment, then that specification, writing it up, putting it in a proposal beforehand, that documentation provides evidence that the questions that we're trying to answer were not motivated by the observed data from a particular experiment. Those questions were specified beforehand, and so therefore the conclusions that we draw regarding these pre-specified questions, they're really more valid, they're more convincing, all right, because they were not motivated by the data. And I would just add to this that, and just giving an example of this, I used to work in the pharmaceutical industry as a biostatistician, a lead biostatistician on clinical trials. And I will tell you that this pre-specification of the research questions to be answered and the analyses, as well as the analyses that will be used to answer those questions. So this pre-specification not only of the research questions, but also of the methods of analysis, the type of analysis, the model that's going to be used, pre-specifying all that is required in the pharmaceutical industry when conducting clinical trials. All right, you cannot get approval in the pharmaceutical industry. You cannot get approval from the FDA to run a clinical trial without having specified the research questions that are going to be answered, the analyses that are going to be used to answer those questions, in addition to just a whole bunch of other information about the proposed trial. So in the pharmaceutical industry, you have to pre-specify all of this information. This information that I'm talking about is contained in what is called the SAP, the Statistical Analysis Plan, which is itself a part of a larger protocol for the proposed clinical trial. So the protocol talks about the entire proposed clinical trial. Part of that is this document called the Statistical Analysis Plan, which goes into a great deal of detail about the statistical aspects of the experiment or the clinical trial. And so the fact that the pharmaceutical industry or the FDA requires this, all right, this pre-specification, this is one reason why the clinical trial represents really the gold standard when it comes to doing experimental or interventional research. So those are the prospective purposes for experimental design. Let's look at some of the retrospective purposes. So the design of the experiment actually, let me back up, the design of the experiment that is actually conducted determines the proper method of analysis, all right? And so to identify the design of the experiment that was actually performed, so that's something we need to do so that the corresponding statistical model can be determined and the valid statistical analysis can be performed. So those are two really important reasons from a retrospective standpoint that we need to consider experimental design. And when might this happen, or when might these issues come up? Well, often and this is not unusual at all. If you've done any statistical consulting at this point, you know this is true. But often researchers come to the statistician only after they have conducted the experiment. Obviously, it's best if they come beforehand so that we can talk about design issues from a prospective standpoint, but many times experimenters don't do that. They come to us only after they've conducted the experiment and they have the data. All right? Now, in such cases, the statistician must ask typically a bunch of questions of the researchers to determine the design of the experiment that produce the data. So that's one scenario. All right, this scenario where they did not come to the statistician beforehand, they conducted an experiment, they have the data, and then they come to the statistician's office and then want help analyzing the data. Well, in order to do that, the statistician needs to know how the experiment was conducted. In other words, the statistician needs to know the design of the experiment. Now, even when a researcher has worked with a statistician beforehand, right, come before the experiment, talked about the experimental design, maybe they laid out a really nice, well-defined experiment, set it up, and then the researcher went out and performed the experiment. Even in that situation, it's very important that even after the experiment has been conducted, that the statistician discuss the conduct of the experiment with the researcher. And the reason is because oftentimes, when a researcher goes back into the field or goes back into the clinic or wherever they're doing their research, wherever they're doing their experiment, there are things that necessitate altering the experiment, deviating from the experimental design. All right, and sometimes you just cannot get around that. Maybe some things, maybe it's an agronomic type of experiment, and things happen out in the field that require change. Sometimes, the certain aspects of the design that seemed good on paper, that seemed good when sitting in an air-conditioned office, really don't work out when you're in the field. And so there are all sorts of ways that this kind of thing can happen. Maybe you're running a clinical trial and certain people go off protocol. Instead of taking the treatment that they were assigned to take, maybe they take something else, or maybe they take something in addition to their treatment. And so, all those kinds of things can happen. And when those kinds of things happen, when a researcher has to deviate from a protocol or change how they were going to do the experiment, then that leads to a potentially different design. Maybe a slightly different design, or it could change it drastically. And so the statistician needs to know about all these kinds of things, because again, the design determines the proper method of analysis. That's one of the big points in this course. All right, this is the reason why we look at all these different experimental designs, because the experimental design that was used in an experiment, whatever it happens to be, that experimental design determines the appropriate method of analysis. All right, and so that is why it's so important that whoever is analyzing the data, whether it's a consulting statistician or the researcher themselves, they need to be very clear on what the actual experimental design is. All right, now let's talk about the components of an experimental design. And so in general, when we talk about an experimental design from the standpoint of statistics, there are factors or treatments whose effects are to be studied via the experiment. There are experimental units to be used in the experiment. These are the experimental units comprise the experimental material that the factors or treatments are applied. There are potentially also, and often are, groupings of experimental units that are used in the experiment. We also need to consider, as part of the experimental design, the manner or the way in which treatments are randomly assigned to the experimental units that are used in the experiment. We also need to think about the means of carrying out the randomization. That's not something that we want to gloss over. We want to be very careful and think about how we're actually going to carry out the randomization. Okay, next let's talk about concepts and terminology associated with experimental design. And so here are some of the terms that we would use. So an experiment, let's just define that first. So an experiment is a planned inquiry that will generate empirical data from which well-defined research questions can be answered. A factor is an intervention or condition, the effect of which is to be assessed and evaluated in the experiment. Then associated with a factor, we have the levels of a factor. These are the various values of a factor that are used in an experiment. A treatment, or more commonly a treatment combination, is a particular combination of the levels of the factors applied that are actually applied to an experimental unit. So we have a factor, one or more factors. Those factors typically have at least two levels. And if we've got more than one factor, then we're typically, or at least in many cases, looking at combinations of those factor levels, and we call those combinations treatments or treatment combinations, and it's those treatment combinations that are applied to experimental units. We then also talk about, in the context of design, we talk about homogeneous or homogeneity. This is, when we talk about homogeneous, we mean a uniform structure or composition throughout, homogeneity being the quality or state of being homogeneous. And then we also talk about heterogeneous, consisting of dissimilar or diverse ingredients or constituents. In other words, really the opposite of homogeneous, not homogeneous. And then heterogeneity, the quality or state of being heterogeneous. And so that comes up when we talk about things like blocking. An experimental unit, okay, so this is the piece of experimental material to which a single trial of a treatment or treatment combination is applied. So again, we have experimental units. These are the people, the subjects, the animals, the plots of ground, or whatever that we're using in our experiment, and to which we are applying a single application of a treatment combination. Now, associated with an experimental unit, and similar to it, but potentially different, is what is called the sampling unit. Now, this is a part of the experimental unit from which a measured response is to be obtained. Now, sometimes the sampling unit is the same as the experimental unit, but sometimes the sampling unit is a fraction of or subset of the experimental unit. And in fact, sometimes researchers will take an experimental unit and partition it up into two or more sampling units, and then sample from each of the sampling units. Now, one of the reasons we need to be careful that we understand the difference between an experimental unit and a sampling unit is that we need to be able to know how to handle the situation where the observations that we're looking at are from sampling units as opposed to experimental units. So we need to make sure that we're analyzing the data correctly in that situation. Now, a block is a group of, and I have a little typo here, but it's a group of experimental units that are hopefully homogeneous. I mean, the whole purpose for blocking would be to get a group of experimental units that are in fact homogeneous. But we'll talk about that there are situations out there where researchers construct blocks or define blocks, but they're really not defined in a way that would make the experimental units within the block as homogeneous as possible. So blocking in and of itself does not necessarily mean that the experimental units within the block are homogeneous, but that is certainly the goal. That would be the goal of blocking. So block is a group of experimental units that are hopefully homogeneous. Blocking is the use of blocks in an experimental design. Now, another term that is sometimes thought to be synonymous with blocking is replication. Now, a replication is the use of a given treatment combination more than once in an experiment. More specifically, it's an independent application of a treatment combination in an experiment. Now, I just want to point out here, and we'll talk about this more later as we get into designs where we have blocking, but blocks and replications are not necessarily synonymous terms. There's one situation. There's one type of design where a replication is the same as a block and vice versa. But there are many examples where the number of blocks in an experiment and the number of replications are different. And so we need to understand from the outset that the number of blocks and the number of replications are not necessarily equal. It depends on the design. Another term would be experimental error. So this is the difference between the deterministic effect of a treatment combination and the measured response on an experimental or a sampling unit. All right, so when we apply treatment combinations to experimental units, there is a deterministic effect on the experimental unit. But there are other characteristics or features of the experimental unit that impact the response variable that we're measuring. And so those other characteristics and features beyond the treatment combination that do impact the response variable, all of that together is the experimental error. Experimental error is the deviation between that deterministic effect that is caused by the treatment combination and what we actually measure on the experimental unit. Randomization, this is the process of randomly assigning treatments to experimental units, and there are many ways of randomizing. That's what really differentiates the various kinds of experimental designs, the different ways of randomly assigning treatments to experimental units. That typically is what identifies or specifies or determines what we might call the design structure of the experiment. And then there are a few other terms that I'll throw out there at this point, but I'm going to hold off on defining them until we get into the appropriate sections. But one term would be aliasing, and the other term would be confounding. So we're going to be looking at those and defining those terms in context. So replication is one of the concepts, one of the terms that we are going to be talking about. Let's talk briefly about the importance of replication. So think about an experimenter doing an experiment, and they apply certain treatment combinations to the experimental units in their experiment, and they get values for the response variables, and they want to evaluate that data, evaluate those responses, and make a determination as to whether or not and to what extent the different factors impact the response. Well, unless a researcher knows the exact values of the variances of the error terms in the statistical model that is associated with the design of their experiment, or they have access to a reference data set from which estimates of these variance components can be determined, then replication is going to be absolutely necessary in order to estimate the variance components of the error terms in the model. Now, let me just say here, so unless a researcher knows the exact values of the variances in the error terms, well, they're never going to know that. Okay, so we can rule that out from the get-go. Or if they have access to a reference data set from which estimates can be computed. Well, they may have that. There may be situations out there where a researcher, maybe an agronomic type of researcher, has data for a particular set of fields over many years, maybe over many decades. And so in that kind of a situation, they may be able to, using that data, come up with a fairly reliable and trustworthy estimate of the variance components for a particular situation. But even then, one could argue, well, maybe you've got data from 10 years, maybe over the last 10 years, over the last 20 years, or something like that. But, does it really apply to the situation right now? Remember, what we're trying to do is to convince people about the results that we come up with, all right? And so we need to think about what would be convincing to those who read about the research. So in the absence of knowing the exact values of the variances, okay, that's never going to happen, and in the absence of having a reliable reference data set, then replication will be absolutely necessary in order to estimate the variance components of the error terms in the model. Now, why is that? Well, replication is necessary because estimates of variance components are obtained from, when we analyze the data, they're obtained from the variability of things that are treated alike in the experiment. Well, what that means is that if no experimental units are treated alike, that is, if you don't have two experimental units that receive the same treatment, then no two experimental units are treated alike. And so if you don't have that, then there is no replication. And so then in that case, the error variance components cannot be estimated, at least not without imposing assumptions, which may or may not be true. All right? And we will talk about situations like this where we maybe make some assumptions, as long as those assumptions seem reasonable, that would allow us to come up with estimates of the variance components. But we typically don't want to have to make those kind of assumptions, and those kind of situations really are only in those situations where the researcher did not come to the statistician beforehand and they design an experiment for which there was no replication. So that's not a good thing. That's a bad thing. You never want that to happen. And so that is why replication is necessary, because replication allows us to come up with estimates for the variability associated with the experimental error. In particular, it allows us to estimate the variance components of the error terms. And we need that to determine whether an observed difference between two treatment combinations is statistically significant. That's what it boils down to. We have an observed difference between two or more, well, in something like this, the difference between the difference in the observed values of treatment combinations, and in order to determine whether or not that observed difference is statistically significant, we have to have estimates of the error variances and then use those to come up with values for the standard error of the estimated difference. All right, so that is why we need replication. Replication is extremely, extremely important. And then let's talk about, finally, let's talk about the importance of randomization. So randomization is important. This is so important, all right? And independence, is important in all this. So we really need to think about, this and understand this. This is not something that we can neglect in an experimental design, and that a researcher cannot neglect it when they conduct the experiment. So one of the primary reasons why randomization is important is because randomization eliminates researcher bias, at least in the allocation of treatments to the experimental units. All right. The second reason is that randomization, the act of randomization, all right, and what we're doing when we talk about randomization, what we're doing is actually injecting. We are intentionally injecting into an experiment randomness. By doing that, we create the probabilistic framework from which or within which valid inferences can be drawn, right? And this is so important. We need to be able to. We want to be able to make valid inferences. Those are the only inferences that will carry any weight, valid inferences. Remember, what we're doing is that we are taking the observed data that we obtained from an experiment, and we are trying to generalize that to some general situation. Maybe it's a general population, or maybe it's a general process. So we're going from the specific to the general. We're reasoning from the specific to the general. That process is called induction, or in statistics we call it statistical inference, but more generally in logic it's called induction. And we want that process to be valid, right? And so randomization is required in order for our statistical analyses to provide valid inferences. If randomization is not used, and this is a fairly strong statement, but we need to understand it. If randomization is not used in an experiment, let me see here, let me go back. So if randomization is not used in an experiment, then no valid inferences can be drawn from an experiment. It doesn't matter how complicated your statistical analysis is, how fancy it is, or anything like that. If randomization is not used, then what has happened is you've not created that probabilistic framework within which valid inferences can be drawn, and so no valid inferences can be drawn from that data. And so that would be a very bad situation to be in. The other problem, if randomization is not used, is that there's no guard, there's no protection against researcher bias in that process of allocating the treatments to experimental units, all right? Now, we'd like to think that researchers are always honest, but look, let me ask you the question. How much confidence would you place in the results of an experiment performed by someone that you do not know, or maybe somebody that you do know, if you knew that randomization was not used? There's always the potential that somebody, they're trying to show that their new drug or their new widget, is better, for some purpose. And maybe, who's to say that they didn't give the most promising experimental units, that new drug, or apply their new intervention to the most promising, the best looking experimental units. So, when we're trying to evaluate the research of other people, typically, whom we don't know, we've not done the work with them, then we need to have confidence that the process that they used, all right, is going to lead to statistically valid results, that it's not biased in some way. And that is why randomization is so important. And so, randomization is, it's not the same as arbitrary allocation. Randomization is an intentional process, right? It's something that we have to do, and there are a variety of ways to do it, but it's still an intentional part of the experiment. And so it's something that we really do need to consider when thinking about the experimental design. And if somebody is writing up a statistical analysis plan or writing up a protocol for their experiment, it really pays off to discuss how randomization is going to be performed, and then to use that, to be sure to use that when they conduct the experiment. Now, let's just talk briefly about a few examples of experimental designs that we will be looking at, and there are more than these, obviously, but so when we think about experimental design, we can think about the design structure of the experiment, and we can also think about the treatment structure. And the design structure and the treatment structure of an experiment, along with the method by which treatments are going to be allocated to experimental units, that really constitutes the experimental design. And so some examples of treatment structures would be the one-way treatment structure, which is what you would have seen in your first methods class. In your subsequent methods class or classes, you may have seen two-way treatment structures, or maybe even higher order treatment structures. When we talk about more than one factor, we're often talking about factorial treatment structures. And when we say factorial treatment structures, what is implicit is that we're talking about complete factorial treatment structures, as opposed to fractional factorial treatment structures, which is that third type of treatment structure listed here. So in many situations, a researcher is going to use a complete factorial treatment structure in their experiment, but there are many situations, especially when there are a lot of factors that a researcher wants to use, that it almost necessitates using some form of a fractional factorial treatment structure. Now, associated with any of these, we could also have one of these, one of these kinds of treatment structures, in addition to having one or more controls. And so, and when we talk about the controls kind of being outside of the other combinations, so outside of that factorial treatment structure. So those are examples of common treatment structures. Some common design structures would be the completely randomized design. Again, this was a design that you probably were first introduced to, the most simplest really of the designs. Then we have the randomized block design, the randomized complete block design, the Latin square design. That's another type of design. You can also have a Latin square treatment structure. I did not include that up above, but you could have a Latin square treatment structure. You could also have there are split plot designs. There are designs called strip plot designs, and there are especially used in, for example, clinical trials and in some animal type of research, you might have crossover designs. So there are a wide variety of design structures, a wide variety of treatment structures, and again, when we talk about experimental designs, we are typically talking about, or we can really specify that by specifying the design structure and the treatment structure of an experiment. So that is my overview, my introduction to experimental designs. In the next lectures, we're going to be getting into specific topics, specific designs, and so we will pick up the material in the next lecture.